a data migration exercise that we did at MadStreetDen. This was about on a production system which had live incoming traffic. And we'll look at and discuss challenges that we had faced during the course of this migration, and what are all the things and the nitty-gritties that we sort of had to take care of. Yeah, so that's the basic idea of what we're going to discuss now. So it's just us. So Madhunisha is basically a software engineer. She works on search systems, Elasticsearch, and all of those things. Basically, what powers Vue.ai and other solutions of us out there. And then it's me, Praveen. So hi guys. I do platform stuff and infrastructure and engineering things in general. Yeah, so that is basically just the quick introduction of us. If you want to ask some questions offline, maybe you can reach out to us on LinkedIn as well. But we'll get right into it. I'll just start by setting the stage for the problem statement. Okay. So like we just discussed now, our basic idea was that we had to migrate data from across different RDS instances or Postgres instances. But what we were put against was that we had to do a major version migration, right? So major version upgrade of sort. And to set some context, we use PostgreSQL to store catalog data, which is basically what our search solutions and other things surround around. Ideally catalog data that empowers e-commerce websites and other things. We can also call it inventory data. So that is what we used to store in PostgreSQL just for real-time use cases where you need to get those metadata out there that will be displayed in UI and other things of our clients' websites. And that's what we stored in PostgreSQL. And this exercise that we did was around back in 2018, just 2 years or 3 years from now. So we were on 9.x version of PostgreSQL. And our challenge was to move on to 10.x version. And the reason why it was a challenge for us is because there were security vulnerabilities that PostgreSQL itself highlighted, and basically asking all of its vendors to sort of move on to the newer version because they wanted to get rid of that security vulnerability. And that sort of also makes sense for a business point of view, that you don't want such activities to happen in your accounts or in your cloud accounts and etc. So just to avoid that, this was an unavoidable sort of an exercise that we had to take over. And that's basically why we also went on for it. And well, that is basically why we had to take on this exercise. There were other things surrounding the exercise itself and surrounding the problem itself that we wanted to address. Because without addressing those, we'll sort of slip onto a gap where the business will get affected in all those scenarios that we did not want to get into. So the scenario is, or the situation at that point was that our PostgreSQL systems will always have live traffic coming to it. There was no way to stop it, or we should not be able to basically halt live traffic for that time. We did not want to do a maintenance window also, because at that point we were on a very good home run of sort, because we had a lot of clients coming in, and then we wanted to sort of always maintain that good rapport with them, and also basically address this particular security patch as well in the same time. In terms of regions, we were across 3 regions. Now we are in a little bit more, a couple of more regions added to us over the 3 years. But back then we were in 3 regions, and our entire stack was on AWS at that point. And all our PostgreSQL instances were simply hosted on RDS. So that was our basic scenario. And one other thing to touch upon, while we do major version migrations across databases, there are points where we might not be always having backward compatible upgrades, right? It might be even coming from PostgreSQL itself, or instead of something that Amazon would introduce within RDS, it might be just a PostgreSQL upgrade, but that could still break your system of sort, corrupt your data, and you might lose data and all those things. So there are very easier ways, or a lot of easier ways that we could have taken on and easily done it off. But our challenge was basically this: always keep serving live traffic, no downtime, and have a homogeneous and seamless migration that we wanted to do. So it's homogeneous because it's from Postgres to Postgres. So that's basically it. Yeah. And yes, talking about our catalog data that we had in PostgreSQL, I just described why it was important, because it is client facing. More than it being client facing, it's more of a user based facing scenario, where if we sort of corrupt our data, the users that are going to be using all of our clients as e-commerce websites will probably be looking at data that is not right, or will not even get a good response in return, which will probably cost them a lot. And that is one of the pain points that we wanted to do. And we store a lot of data in PostgreSQL because we kind of leverage its indexing speeds, query speeds, and all of those things. And we sort of understand PostgreSQL a little bit better than other solutions. And it serves a lot of good purpose for a real-time scenario. Yeah, okay. So we call our PostgreSQL machine that basically does inventory storage Watchtower. Just a quick backstory about this is that a CTO Anand basically introduced this concept where most of our microservices, actually all of our microservices that we build, will all be named after DC characters, DC being DC Comics. And that's why this Watchtower is basically one of the Watchtowers where all the comic characters come together and then sort of collaborate and do all of those things. And that's why we also named it after Watchtower. And Watchtower is where we store our inventory data. And these are key points because we will sort of revisit this at a later point and also talk about what the challenges were in terms of what the use case and scope of Watchtower is. So it houses inventory data, it is indexed for faster queries, and it also serves real-time data APIs, basically what the front end will see. So why would there be a real-time data API if there is a search solution that we already have? It's basically because search systems are also interdependent on these data APIs. They kind of rely on this data that is there, and Watchtower is basically our source of truth for any inventory data that we house. And that's basically the reason why we have a real-time API as well. And to Watchtower, apart from reads, writes happen at a very greater rate. It's over like 100,000 records per minute that's being upserted into the database itself. And the reason being we're across a lot of 3 regions and all those things come together. A lot of requests are going to be abstracted out of different data centers and all those. And that's basically what Watchtower is about. And just to give a quick understanding of what the system is and give more clarity visually. So in the right side of it, we see streaming upserts. To the left of it and to the bottom of it, we see read requests coming in. So to explain Watchtower, this is basically very simple. Back in 2018, we did not have containerized systems in place. We still were on EC2 machines. That's basically M5 large or M5 2x large machines at that time, which will basically read from Watchtower. It was an API because we wanted to control what sort of data goes in and comes out. We had very rigid sort of a schema definitions that we have in place so that it can be, we always are sure about what data goes into the system instead of that being served as a library of sort. And also authentication and other things that we can imagine of. Not that dealing with databases directly do not have SSL and TLS, but this was just another layer that we wanted to have our own sort of logics to authenticate what client, who, and what. So just for reasoning and other things. And then comes the PostgreSQL machine itself. We sort of have general purpose for a few scenarios, provisioned IOPS for few scenarios and other things. But Watchtower in general is provisioned IO because we have a lot of network IO happening inside. It's a very large disk space and it's a very big instance generally. And we have streaming upserts. The reason we have streaming upserts is because data keeps changing in near real time. The product that someone would have bought 2 minutes ago should probably be out of stock in our metadata store. All of those stock management and some of those principles are also being served from Watchtower itself. We don't do that heavily, but those are also scenarios that we sort of serve. There are also regional dependencies that we do. Someone visits a particular e-commerce website from a different region, and they hit Watchtower for getting some information out of it in a data API or sort. They get a different data, and region 2 gets a different data. All of those things are logics that have been written around this particular database. And that's why streaming upserts are important, because we wanted to always refresh the data as soon as we can. and our SLAs are very decent in terms of how the turnaround time for a packet getting into the system and being in this for queries that we need to serve. In the below or the bottom point, what we see is all our microservices. So when I mentioned search systems earlier, we have like an in-house search system, a combination of in-house search system and open source search systems like Elasticsearch and other things. But our in-house search system, which basically powers a lot of our search solutions and Vue.ai, Vuex, or whatever other products that we have, are basically the microservices that are going to be querying Watchtower for its purpose of providing latest recommendations for a particular product or latest recommendation for a particular user and all those things. Yeah, and that is another thing that's going to be querying Watchtower. And there is also ingress of sort, which is going to be coming from rest of the world. Obviously, that is going to be very high traffic that we wanted to serve. So it's obviously behind a load balancer. We don't go for API gateway. It's just a load balancer that's going to be distributing traffic across M5 large machine. So that's basically serves a use case. So we just went on with ALBs. So this is basically to give us an idea of what Watchtower is, why it's important, and etc. And the pain point here again comes back to what we were trying to do. What we were trying to do again is to, while having streaming upserts, keep migrating data to a different machine. So the only way that you can probably think of migrating in this particular scenario is that there is a machine which is 9.6 with us right now, which has data already. The only way we can do it is clone this database to a newer version of Postgres. But at the same time, both of these machines need to have data which is going to be in sync always, or at least in near real time, right? So that is basically our problem. And the way we chose to solve it is just from the problem definition itself, you can basically infer that it's a replication problem of sort. And that's the reason why we chose logical replication to be our solution for the problem that we were trying to solve. Just to reiterate on why logical replication is because writes are going to happen at the same time reads are going to happen. Writes cannot be stopped, reads cannot be stopped, and there's a major version that's going to happen. So that's that, and at the same time we need to have 100% uptime serving all requests within the microservices across the data centers and also to the clients. And logical replication basically for us is the best possible solution at that point, and that's why we went on with logical replication. So I'll just let Madhu right now explain what logical replication means and how it relates to the problem a little bit more in a broader spectrum.
Thank you, Pradeep. Okay, so before jumping into the topic, I'd like to apologize because it might feel a little weird if I'm not looking into camera while talking. So I'm connected to my external monitor due to some laptop issues. Yeah. Okay. So thanks, Praveen. So now that we've got an idea about what the problem statement is, the first thing which we should be thinking about is how we are going to be replicating the data, right? So at high level, there are two different types of replication, if you are aware. It's physical replication and then the logical replication. Okay, we'll see why we have chosen logical replication over physical replication. If you see, one drawback of physical replication is that it will just allow us to migrate the entire database, meaning it will not allow us to make a selective replication. Instead, it will make us migrate the entire data, which is kind of noisy, right? So we might have to migrate the excess data more than what we actually want. So that's not the case here. Also, physical replication will expect the target database to be kind of identical to the source database itself, and also it doesn't support the target node as a writable node and so on. So those are like kind of pain points with respect to physical replication itself. So with respect to to highlight on what is like better in logical replication is that it allows us to send incremental changes, so which is sort of what our use cases. So even when the writes are happening, we'll have to make sure we migrate all the ongoing replications as well. And also it supports cross-version migration, because now we are dealing with migrating data between different Postgres versions of RDS. And also it makes sure that it supports transaction consistency, because the data will be written in the same order as the source data. Yeah. Okay, so yeah, so what is logical replication? As the name implies, it's a strategy to replicate the data objects and all the ongoing changes based on a replication key, which is a primary key. So if I say data object, it also includes the large objects. Hope you guys are like.
Just 1 second, sorry. Are you changing slides? I only see the logical replication slide.
No, I'm just talking over the same.
Oh, okay, sorry. Go ahead, please.
Okay, so yeah, so I'm talking about large objects as well. So we have like certain strategies where we'll be migrating large objects. We'll cover that in our upcoming slides. Okay, so how are we going to be doing this logical replication? As you can see, it's a two-step process, right? So the first step is table synchronization phase, and then the next one is the change data capture, which is CDC, where we'll be capturing all the real-time updates. Okay, so the first step in the migration process is migrating the existing data itself. Later, we'll be migrating all the ongoing replication, which is what our problem statement is. So in the table synchronization phase, what we'll be doing is, so we'll be taking a snapshot of the source RDS, and then we'll be copying it to the target database. Meanwhile, what we'll be doing is we'll start capturing all the ongoing replication in a replication slot. So DMS will make sure it creates a replication slot in the source RDS, and then it will start capturing all the ongoing replication when the existing data migration is happening in the table. So you can see here, right? So the first diagram shows that shows the full load synchronization, which is the first step in the logical replication. So we have two records in source table. So we'll be copying the same to the target table. In the second example, you can see that. So when the migration is happening, we have got two more inserts in the source table. So what will happen is the replication slot, Postgres replication slot will start buffering the records, the inserts that had happened during the migration. And then once the snapshot copy is complete, which is a second, as a part of the replication process itself, will start migrating the change data which are captured in the replication slot to the target database. So that's how the logical replication is being done here. So to give an idea about what replication slot is, so I hope you are aware of the primary and primary node and the replica node in any database, right? So whatever changes made to the master, the primary node, will be replicated to the will be constantly updated to the replica instances. Sorry, replica nodes. That's where replication slot comes into play. Same strategy is being used by the DMS as well. Just that all the ongoing replication will be captured in the replication slot using val logs, the write-ahead logs, and then it will be migrated to the source database. So this is how a logical application will happen. Okay, so as a part of the migration process, we actually evaluated two popular migration services in the market. So one is DMS, which is AWS service, and then the Dependencies. So we'll see which database actually suits our purpose. So AWS DMS is like a managed service by the AWS itself. So it's a serverless tool. But as opposed to that, Dependencies is a self-managed tool, so which will involve some manual intervention with respect to scaling or few other cases, right? So will not expect any DMS will not expect any kind of support from any user. Support as in will not require any manual intervention. And then the other comparison can be in Dependencies, global read lock will happen on the source database when the migration actually happens. So any read that happens to that is made to the source database will not have the updated record. Meaning, if any writes happen to the database, and then if you are trying to read database with the updates reflected, will not happen because lock will be made in the source database. But that's not the case with the AWS DMS. And also in Dependencies, we have additional dependencies like Zookeeper, Kafka, so which is an overhead to actually maintain, because Kafka will be used to stream all the data from. So the Dependencies connector will make use of Kafka to stream data to the target database. So we did not have any bandwidth to actually support Zookeeper and Kafka in our migration process. So we thought it would be better if we had no dependency. So DMS actually supported the same. And then scaling is kind of a cumbersome process because it's a self-managed tool, as you can see. So we'll have to support, we have to manually configure any scaling if needed. So that's not the case with DMS. And also Debezium comes with an additional maintenance cost as it's a self-managed service. But then with DMS, we just have the replication instance cost. Yeah. Okay, so here are a few key features with respect to Amazon DMS: migrate, serverless, and low cost. Migrate. So, the types of migration which actually DMS supports are listed there. So it says it supports migration between different cloud servers, and also to port data between different physical servers within the AWS account itself, and also it supports homogeneous and heterogeneous migration. The migration which we are going to be talking about is the homogeneous migration, because it's migration between the same data store, just the version migration is happening. Heterogeneous migration will help us migrate data from a different data store itself. Say, for example, migrating data from a SQL server to Elasticsearch, or from Amazon Aurora database to Elasticsearch or Postgres or whatever it is. So this is how. So these are all the kind of migration that is supported by DMS, and then it's serverless, like it's fully managed by AWS itself. So it will guarantee high availability when we are actually performing the continuous replication. And then it's low cost, because we are just going to be paying for the replication instance we have launched. And then the cost can be as low as $3 for a 1 TB sized database. So it's like, so it's also cost efficient when compared to that of the other migration services in the market. So yeah.
Okay.
I let Praveen talk about the migration strategies which we are.
Yeah. So before we also get into migration strategy, I would like to stop here. If there are any questions, we can also take that. I understand that this was only about just problem statements and what DMS can serve for us, but we'll be happy to clear any doubts in terms of these two things. Let's wait for a few seconds and then continue. Okay. Okay, yeah. If you have any questions, just post it. I'll just keep a tab on the Q&A tab. Okay, so far as migration strategy goes, this is basically it. So this was, to put it in a nutshell, this is it. Right? So, but there is a lot of action behind the scenes that we also have to take care of. But in general, continuous replication, because the writes and reads are happening in parallel. And continuous replication will basically take care of a full dump that's going to be moving from source to target. And after that dump is over, you can also buffer all the streaming changes into target also, and then apply those changes as well. The reason why this helps here is because, like we spoke, Debezium will do a read lock on source database. You won't be able to write, or you have to sort of strategize around writing to a new table and then sort of merging these two together, or reading from two different tables and all those things that you have to take care of. But in terms of what we were planning to do, is continuous replication is going to take care of both of these things in a slightly different way, where we only needed to configure all of these things a little bit more carefully and get off with it. And the next is, after we migrate data, and then we already have a clone, and like I said earlier, we have a synchronous database across two different engines, database engines, Postgres 9 and Postgres 10. You will have to sort of slightly shift traffic to the newer machine, so that we, in the first place, warm it up so that it can take traffic. In the second place, be able to make sure that your traffic is being served well. You can do quality analysis, you can do metrics that will help you understand if the traffic is being served with OK requests, or if it's being responded with bad requests, and all of those different things. So as long as our A/B tests are going to prove that A and B are both equally healthy, we'll slowly incrementally shift towards B, and then we do off with whatever reads that we want to do with B alone, which is basically the new machine that we sort of launch. But during this process, we already need to sort of write new changes, because anyway, it's going to be replicated down to the new engine. We can still continue reading from the new engine, but the writes still have to happen to the new or the older engine, because writes can't be replicated two ways or both ways. It won't be bidirectional. It is unidirectional, such that writes will always be done from left to right, ideally from older machine to newer machine. So writes still have to continue writing to the older machine, only after we are sure that we can migrate completely and decommission the older one, which is basically A here. Only then we'll switch rights to the newer engine and then basically decommission the older one and then do off with it. So that is basically the plan. And I think this basically worked out pretty well for us. But just putting it down on paper and then theoretically just looking at it made it look a lot easier. But there were a lot of nuances that we sort of had to understand and then also play around with. And DMS, basically database migration system that AWS had, was not that mature at the time. Right now it has 3 years extra, and then they have done a lot of changes in terms of how they can perform well. But at that time they were just coming off as a new migration engine. Their primary focus at that point was mostly about bringing people into the cloud, and data was a friction point because if you can't move data easily into a cloud, then you probably won't spend that much time in sort of doing that migration. There is a lot of overhead there, and that's basically the reason why they came up with DMS. And we sort of used this for a homogeneous migration where we went on from Postgres to Postgres within RDS within the cloud, and that's basically something that they were also amused to listen about. Because they never thought that they would use it this way. We generally had a partnership with them so that we spoke to their support and then sort of got an idea how, if at all our strategy is well and good. And their technical support team was basically, they had not seen this earlier, and they were quite amused that it can also be used this way. And they supported us throughout, and we'll talk about what all went down, how much time it took for us to basically do this, and the nuances. I'll just give a base again on the constraints, because this is important in terms of what we had to address. The major two constraints here earlier was that there is going to be read and writes happening throughout. But the other things in terms of migration itself is that migration can be costly at times in terms of breaking the system because of all of these things that we see here, which is there is going to be a huge volume of data because we have a lot of inventory data that is there. We have like a few of our customers have like 180 fields or 200 and even close to 300, 400 fields of which we had to index and all those things. So the data volume was very huge. 500 GB is basically just in one region. That is going to be triple of that across 3 different regions. And at times it is very imbalanced, and it is sort of skewed across different clients because different clients have different inventories and all those things. And moving it one chunk at a time per client will also not make sense for us, because we wanted to sort of do it off at one stretch so that we don't have to mess up data or different types of systems, manage 2 different systems, and then basically have that overhead in place. So that was our plan, to basically take it all at one shot and then do it off with that. And our collections are also another affecting factor, because the volume of data that we had could have been 500 GB or 1000 GB, but the real problem is it is spread across multiple different tables, right? So if it was 500 GB of data across one table, it would have been very simple for us because of the things that we would see in the upcoming slides. But because it is across 3,000 tables, and there were like so many sequences, and there was also so many schemas that we had to migrate, each of these things mean different data, and each of these things have different sort of state maintenance that Postgre itself does. So that is basically one other problem that we have. Okay, so Shiva has a question. How long did traffic switch take? Do you have issue with lack of read-write consistency during this period? Okay, I'll just come back to that question, but I'll come back to that question. Yeah, so we were just talking about the constraints, and there is also throughput, which is going to affect a lot. The read throughput on source database was really high because our incoming request was high. Like Shiva is basically questioning at this point, our read throughput was about more than, it was matching the number of writes, and if not, it was twice as much as writes that we had. This, I'm only talking about the client side of things, right? So if it is combined together with microservices and the client-facing scenarios, it would easily cross over 200 to 300,000 requests per minute. And at times, this is the average thing. In peak, we did more than 350 to 400. Sometimes it would cost 600 because we sort of index our search engines. And then for indexing our search engines, we need metadata to index the search engines, and all those things were in place. So all these batch processes at a particular peak time will have over 400,000 in average. In general, it had 200 to 300,000 per minute that we served over our APIs, right? So all of our APIs are mostly dependent on data. So it is basically any request that comes in translates to a request to the database. And migration would require more network bandwidth because of this very reason. Because not only that we are already serving so many sockets that are live, we're also going to serve another set of sockets, another set of buffers that is going to migrate data continuously out of the source database. So this puts us under pressure where even though we're migrating data in real time of sort, and then we're replicating continuously, all of these things are happening. We might put the source database in trouble because it's going to take another additional load, which is the migration process itself. But we'll see how we handle it. And there are also indexes, and indexes are basically what we rely on in terms of our speed. We have B plus tree and just indexes for different purposes. Just for JSON-based indexes, and B plus tree generally what Postgre suggests, right? So it's for any columns that has text-based. Just will be our JSON-based that we wanted to index. And index size itself was about 100 GB. And we can easily cross 200 GB just by adding in a couple of more data, or having another client come in and then say, I also want to have my data stored in this particular place so that I can also power my metadata with it. So indexes grow very fastly. We sort of have archival strategies and other things so that we keep indexes as small as possible. And it's 100 GB right now. We have like we have a regular process of maintenance where we do vacuums and all those things so that it's always kept at 100 GB or somewhere around 100 GB. And that's basically the constraint that we had. So with this constraints, I'll just quickly jump ahead with what logical replication is. But just keep in mind that these constraints are always going to be there for us, even if we wanted to sort of bypass a few things here. We would probably put the source database in danger, or all our incoming traffic in danger, right? I'll address the other point of how long it took for us to switch from source to destination, but I'll just go on explaining the replication, come back to it at the end. Logical replication is basically like Madhu basically said. It has a concept where it can do replication in real time, but the key part of it is what we see here, the replication slots and write-ahead logging. Write-ahead logging is anything that we see in most of the databases like MySQL or Postgre, or even Aurora has wall logs. But why this is important for us right now is because consistency is very key. Though we can basically say, yes, we did migration with no downtime, the actual merit to a migration being fully complete would be that data is sane across two different engines, right? So data sanity has to always be there, and data has to be integral at all times. We can't have different data and two different systems for the same records, and that will cost us a lot of failed requests, or it'll give us bad quality of results that we serve. And keeping in all of these constraints in place, and having to address all of these constraints, our best go for this was leverage wall logs, make use of replication slots to do the replications, and then implement logical replication such that at any time our T logs, basically transaction logs in source, will always have data that is being returned to it. In the sense, whatever wall log is going to be processing will always be recoverable, right? Because in terms of PostgreSQL and databases in general, there is always going to be disk and heap, and also there is going to be some stuff in memory. But once you move something to the disk, which is basically data files and data binary files, which is what we refer to as large objects and all those things, those are always going to be in place. Even if they crash, we can just restart or reboot the system and then have those data recovered at once. Although we take snapshots are going to be taken in an interval, but we wanted data that is always going to be there with us. We don't want to lose it, right? If we don't turn on wall logs, what happens is there are no replication slots, there are no wall logs. There is only a transactional log that is going to be saved in this way, where you will write something to the database. In the sense, you can write a new record or update a record or have a commit activity that happens on the database, which does not get stored anywhere until the write actually happens on the disk directly. This basically means that the transactional logs that you see and the data that you see on the database or a queryable data that you see on the database are going to be different for a fraction of seconds or fraction of milliseconds, because there's a lag between the data that you send to transaction logs, the change commits and all those things, and the data that you write to the database buffers, memories, pages, and all those things, right? And that's why turning on wall log basically means write first to the transactional log, make sure that there is a log of whatever whatever activity that you're trying to do on the database. Only after there is a successful write to the transaction log, take that changes committed to the database directly so that it is queryable. That basically helps in terms of consistency a lot. And our replication then works on wall to wall, ideally meaning there is a wall sender in source, there is a wall receiver in destination, and the communication in between all of these things are replication slots. So with replication slots, we understand what wall status is, what sort of write ahead logs are there, and on which database and tables these wall logs are operating on. And that can be a replica of or a clone of this particular wall sender sitting as a wall receiver that will only communicate to one wall, so that it has a very common state maintenance between these two walls. And then all those information are going to be routed through replication slots, so that information that is being done or activities that are being done in the source databases is directly being applied in the target database without any failure, right? And even if there is a failure and we see the database does not have that information right away, when you replay the transactional logs, all of these information is going to be popping up. And the same thing will happen in destination because it's a wall-to-wall sort of a replication. And that's basically logical replication, right? Yeah, so this was just to give an idea of why logical replication is here in place for us. Yeah, and okay, yeah, now I'll just pause for Madhu to explain continuous replication and the process that we went on with in terms of DMS.
So yeah, so the continuous replication is what our problem statement is, right? So we make sure we migrate all the full load data, which means the existing data from the source, and then we'll be applying all the CDC we have captured in the which actually were captured in the replication slot, like Praveen explained, and then we'll be migrating the same. So this is a two-step process, like we saw in the logical replication itself. It's like Praveen. Okay, I'll just highlight on the migration settings which we were actually using here. So you can find this in any when you actually create a DMS migration task, right? So these are some 3 critical configs which we should be kind of paying attention to. So the first one is include LOB columns. Okay, so I mentioned that we were actually migrating LOB data as well during this data migration. So as you know, LOBs are objects which are huge in size as opposed to other primitive data types, right? So we may not be sure about how big the data is in the source DB itself. So the default setting, if you see for an include LOB column, is limited LOB in the DMS task setting. So what limited LOB mode will expect us to configure is we should specify the data block, the LOB size itself. So if at all the source database has a record, has a LOB which is has an LOB which is greater than that of which is higher than that of the LOB size itself, then it will result in truncating the data itself. So we might lose the data. So what we have configured here is, irrespective of the LOB size, whatever LOB size we are going to be migrating, we are turning on the full LOB mode. So that's the reason for full LOB mode. And then the target table preparation mode. So here the default setting for this particular config is that truncate table on target. So what this config will do is, will truncate the schema, all the existing records that are present in the target table, And then what it will do is it will try to infer the schema from the source DB itself. So in such cases, there might be a possibility that we might end up having different data types when we are trying to create a schema from the source to the target table. Say, for example, we ran into certain issues where the Boolean data type was not properly migrated when we try to infer the schema itself. So what we went about is we thought of creating a schema of the target table manually in the target database, and then we turned on this do nothing mode, so which will make sure that it doesn't disturb any of the existing records or the schema in the target table, to just migrate the data from source to target. So that's the reason why we went about do nothing mode. And then the next one is stop task after full load. So this is a migration type which we are going to be using, which is the full load migration, right? So first we'll be migrating all the existing data, and then we'll be capturing all the ongoing replication that had happened through the replication slots. So these are all there are other settings as well, but then these are some 3 settings which we should be paying attention, and then whatever we have learned from all these settings. Yeah, over to you, Brian.
Okay. Yeah. So again, I'll just pause again if there is any question before we move on. We basically explain logical replication and other things. Because we also have 15 to 20 minutes right now. We can pause here for a few seconds if you have questions. Yeah, we'd also like it to be interactive session if you guys want.
Yeah, okay, a couple of questions ahead, if you don't mind.
Yeah.
So one was, I didn't quite follow what the schema issue was. I thought you started with a snapshot. So why, I mean, and when you're starting from a snapshot, how do you sort of also create the tables manually? That part I didn't sort of follow what you were trying to say there.
Okay, I'll just take this one. So what we observed while we sort of started the migration is that obviously the first step is to synchronize 2 different databases. But in that sense, we wanted the destination database, which is where we are migrating to, or the target database, to be having that metadata property, in the sense the table schemas and other things and all those. So while we do an initial dump, DMS itself by default will try to do one additional thing, which is basically to infer schema from source. Ideally, if we had a table called table A, it will try to infer schema from table A, try to create that table again in database B, which is our target database, and then try to move data. While this happened with the premature setups that DMS had to follow, they had problems with Boolean information being migrated because they would infer Boolean as string at that point. And that was a support ticket that sort of went on, and then they basically suggested that you could do this with don't stop do nothing mode, which will basically not do anything for your schema migration, and it won't affect the target database. All it will focus on is to move data from point A to point B. And that's why we went on with this approach, where target database is being created by us. Obviously, with the script, we'll just we already know the schema. We'll just do a creation of our tables there. We know all the tables and data types and etc. JSON or not, and then start the migration. So that's basically it. Did that answer your question, Shiva?
Okay, so can you talk about the snapshotting step then? Maybe then something I'm mistaking what you said when you said you started with a snapshot on the target side. Can you explain what exactly what did you do there?
Okay, yeah, I mean, snapshot in terms of what migration is that we took data from, we would just configure DMS, right? So the first point is that DMS itself will do a full load. And for that full load, we had to take care of these things that we generally do, metadata or the target database and other things. Yeah.
Okay, so this is a concept inside DMS, not Postgres snapshot that you're talking about. There's something else.
Yeah. Postgres snapshot would be just at point in time, it will just take a snapshot in that. For this, yeah, I'll just explain one more detail. Maybe that will clear this concept. So when Madhu meant snapshot, it's basically about taking the dump within a transaction. So create a transaction, DMS creates a transaction, and at that point in the transaction, whatever data was available, it will take that data, move it into target database. While it's moving into target database, there is an elapsed time. For that elapsed time, it will during that elapsed time, what it will do is it will keep buffering these change logs that come in and store it in the source databases replication slots itself. Then replay those replication slots and target.
Okay,
And that's where
got
the
it.
replication comes in. Yeah.
Okay, so it's actually like a SQL dump and restore on the.
Yeah.
Okay. Thanks.
Okay. Yeah. Any other questions? I think that was one other. Okay. Yeah. Sure. I'll come back to the consistency. Okay, and then I'll just quickly swift over the slides that are upcoming in the interest of time as well. So there are different variants for in terms of database migrations, right? So small databases and large databases, and we found that DMS behaves differently for different databases, and any migration system like Dependencies or anything will behave differently for different databases because the volume is different. And so for small databases, our idea was you don't have to put too much effort into it. Just keep the settings standard, start the migration jobs. It will migrate from source to target, and then start on replication, right? So because it's a two-step process where you migrate, you take a dump and then restore it to target, and then ongoing replications are being applied. For large databases, the dump itself will sort of cause issues for us, be it WCM or DMS or any other thing. And for these things, what we generally followed was we broke it into chunks. We broke it into different tasks. Each task would take a chunk of that particular table and only focus on those rows, including replication and including dumps, right? Say, for example, there are 100,000 rows. The first 10,000, we probably divided those 100,000 migration into 10 different tasks. Each of it took 10,000 rows, and it will only look for those write ahead logs for those 10,000 rows, and only look for taking dump of those 10,000 rows and then doing migrations and replications. And that basically solved a lot of problems that we were facing with single task and all those things. And that's one thing that we saw. And we had to take care of a few things in our parameter groups that we know of in Amazon RDS. These are basically server properties for Postgres. The first one is not, the second one is. The first one is about letting RDS know that we are going to do logical replication. That basically means that it will create an RDS super user through which you can read all the logs or any server-based logs that generally would be protected. And it will also create wall level. It will set max wall senders to infinite. In reality, it won't be infinite. It will basically be an exaggerated number of sort. And max replication slots will also match the number of senders that you want to have, because they are basically related to each other very tightly. And the sender timeout generally is we set it to 0, because DMS generally uses this particular mechanism where it's going to be reading data from wall logs, right? And sender timeouts are something that signifies how long it takes for a wall sender to send wall logs or write wall logs to T-logs. And that will basically become a problem when sender timeouts are going to be lesser, and DMS is going to be having a connection that reads from these transaction logs. And there is a timeout that happens during this time, and then we lose transaction logs in between. And that will cut a lot of our sanity and integrity that we wanted to address. Sender timeout is 0. But while we have these things in place, we sort of have one problem that I'll just address right now. I think I've already explained what write ahead logging is. So I'll just skip what write ahead logging is and then just talk about these 2 points. So what we do whenever we do an insert or update, right? It will first, when we turn on wall logs in general, it will first write to the wall buffer. The wall buffer is going to take care of the transaction logs and consistencies that have to be in place. Once you write to wall logs, it will then go update in memory data structs, which is basically our data types and all those things in the RAM itself and memory. And then finally go to the disk files. And that's where we get the data files that we want to read from. And these are the data files that any migration system is going to move from point A to point B when we want to do a migration. And for us to know which files we can move, we will refer to replication slots and understand which walls have completed its job and which walls have fully written what files. Understand those metadata about that system, then infer which files to be moved from point A to point B. The problem that we have here while turning on wall and then doing this two-step process, which is basically what we saw in a very previous slide, which is this, is that when you move something from point A to point B, and then you basically say, I'm going to stream all the incoming changes into a buffer in the source database itself. The source database is going to incur a lot of cost in terms of disk size. So whenever we would start a DMS task or any migration task that would move data from our source database would have a really big surge in terms of data disk size. And we have to control that by speeding up the process of the full load step itself. And that's why breaking down tasks will speeden up all of these things. And then the data disk won't run out of disk space, and all those scenarios can be avoided. And ideally just come down to the normalcy, while all of these replication slots are going to be deleted, because replication slot is where our information about all of these things are being stored, and buffered application changes are also being streamed into. And that is one key metric that we sort of kept an eye on, because whenever you do a migration, you don't want to affect your source database. But this is an interim cost that you have to pay on your source database, because that's the only way that you can sort of move data. And the other thing related to this is PG replication slots are what replication slots are. They sort of tend to go in idle state. This is very similar to our connections that we see in PG start activity. Empty connections or idle connections are going to waste a lot of in terms of connectivity itself, because you won't be able to have more connections that you want to do to the database, because there were idle connections or zombie connections that are in place. Similar to that, there are replication slots, but this is in terms of data. So you would have piled up data that would have probably already been migrated, but the process that was doing the migration, which is in our case DMS, would have failed to delete these particular replication slots, which it took care of. And if the replication slots are idle for more than several hours, we would just basically delete it, because we understand that it is being moved, and the status of the replication slot itself will convey. We'll basically be able to understand from XMens and all those parameters that we know of in PostgreSQL to understand all those things. And the next is network IO. Like I said, because our watchtower machines are already incurring so many requests and so many writes and reads and upserts and all those things, and we add another overhead of it by moving data from point A to point B through migrations. There are so many connections being created within the PostgreSQL machine itself for the tasks that we created. And right now we don't have one task, we have so many tasks that we have broken down the entire migration into. So it's going to create more connections now, and network IO is going to be one of the thing. For this, we basically threw money at the problem. We scaled up our RDS instance and then basically said provision more network IO, because there was no optimization at that point that we wanted to do, and we were okay with incurring that cost at that point. But if you had to optimize that particular network IOs, you would probably have to be smart in terms of managing when reads happen, when writes happen, and all those things. Basically spread them out and have a sparse thing. If you didn't want to do that, you would have to just scale it up. Yes, and the second step after migration and then replication, right? At this point, what we have right now would be, you would have moved the entire data from our source database, and we would continue to update all our incoming changes to target database. And now what we would want is a sequence table that we, or can call it a sequence table. It's a sequence. In Postgres, we want sequence to create new IDs and all those things. And at that point, we used Django heavily for most of our microservices. And Django generally just creates sequences for any table that it would generally create. And sequences are not going to be migrated by DMS, right? So it only focuses on tables. So there has to be another process that we wanted to spin up, that after a migration will create sequences. But there was one other catch that we had to do, which also addresses Shiva's question that he asked earlier, the time taken between switching the traffic or switching the writes. So while we switch the writes from point A to point B, and note that while switching the writes, we already know that both the databases are in sync, and reads are already happening from the target database. But there is only writes happening in that source database. While we switch these writes from source to target, there is an elapsed time during which it's basically a blue-green deployment, right? So half of it is going to write to source database, and the other half is slowly going to start moving towards the second database. And while the half of it writes to the first database, your IDs that are going to be, or the values that are going to be populated in the sequence are going to be increasing in source database. Basically meaning you have 100 rows in source, 100 rows in target. Now 50 of your process is going to write to target database, and 50 of it is going to write in source database. Your source database's records will also increase. Your target database's records will also increase. The only good thing here is you don't have to do bidirectional migration, because you're anyway going to decommission source. So that is clear. So whatever data is going to be written in target need not be copied over to source, but whatever is going to be written in source should always be replicated, and we haven't stopped the replication process. So all of these things are in place. But in terms of sequence, when you write to source, the ID, the ID that you create, right? So let's say you're writing 101st record in source, there should be a 101st record being created in target as well. But the problem there is also 50 of your processes writing to target database as well, and that should not ideally create a 101st row looking at the sequence value as 100, which was lastly created. And that's why we basically created a buffer of sort when we created a sequence in the target database, right? So we would generally create a sequence, let's say 100 was our sequence in source database, and in our target we would generally create like 200 as our last known value, because when the 50 process that is writing to database B continues to write, it will start writing from 201, and the 100 process that the 50 process that is writing to database source database, which is going to be moved through a blue-green deployment or the blue instances, they'll start writing from 101 to 200 of sort. So that buffer will basically take care of the elapsed time. And to address, I'll probably just skip this because we are already hitting the time. But just to touch on this, for indexing, we just did a concurrent index creation, which takes care of not locking the source columns and not locking the records and etc., so that you can continue to read the tables, but the indexes will be created over time and not abruptly. For tuning, we just did commit rates and LOB chunk size, which is basically increase the commit rate so that the number of records that you write at one particular commit will be huge, and break down the chunk sizes into sufficient chunks. Basically, move data files in batches of hundreds or something like that, for whichever is optimized for your database, so that it's not trying to move all of the 1,000 files at once and all of those things. Even within a task, it will try to do all of those things. So if you chunk it after you break it down into tasks, it will be much more faster and easier. So I'll just probably stop here. I ran through a few slides, so I'll just wait for questions right now. And before I get any new questions, I'll just address Shiva's question, which was about having issues with lack of read and write consistency during this period. And we did not incur that inconsistency problem because we sort of handled it through the sequences issues and the blue-green deployments that we did. So if that answers your question, it will be fine. If not, I can just explain a little bit more in your,
The question I was, let me sort of elaborate it in case it wasn't clear. Now, there's a period where you're writing to the source database, but reading from the target database.
Yeah.
Right, during this during the sync process. Now, since it's logical replication, it is going to take some delta time for that change to get applied. So I don't know what the application use case is, but where there's use cases where application would just write and immediately try to read the same data, and it would not get the value it just wrote. Right? Because it's reading from the target, but it's writing to the source. Was that pattern at all a problem, or maybe it didn't exist at all?
So that was not a problem, because we would only switch writes after we indexed the entire table, or we would only switch the reads. Sorry, we'd only switch the reads after indexes are being created in the target database. So whatever was indexed from source to target through replication would happen in a jiffy. We'd not have that inconsistency. If we did not create index, writes would be slow even through replication, And at that time, we would see inconsistency issues that you sort of bring up. But that's a good point. Does that address the questions?
Yeah. Did any others have any questions?
Okay. If you have questions that you probably want to post directly at us, also you can just nudge us on LinkedIn as well.
How long did the entire process take, end to end?
Because we had a very big database, it took, I think, so I'll just give for one reason it will take around for us for 500 GB of data. It took us around, I think, 7 hours or 8 hours at max for the migration to complete. For the entire exercise to complete, it will take at least 18 hours or something because it has all of these A/B testing and all these things we do.
Okay. 18 hours is a long time.
Yeah, it is. It is. But the time that we wanted to get it done was 1 day. So we sort of 18 hours was something that we could afford.
Awesome. Okay, I don't think there are any other questions. Thanks, Madhu. Thanks, Praveen. Very interesting talk.
Thank you. Thank you for having us today. We'll look forward to more SaaS engineering talks. We'll probably join us. Yeah.
Thanks for that.
Thanks.
Yeah. Thanks.
Thanks, everyone. Bye.
Thank you, guys. Bye.